Physics-based character control aims to generate physically plausible, robust motion that responds dynamically to varied control inputs. A prominent approach involves learning reusable motion priors from large-scale datasets. However, existing methods face a significant trade-off between expressiveness and task adaptability. While VAE-based priors offer compact action spaces, they often lack temporal consistency. Conversely, recent diffusion-based policies capture long-horizon distributions for smoother motion but are typically trained offline. Integrating these diffusion priors into downstream tasks usually requires loss-based guidance or iterative optimization at inference time, which demands differentiable objectives and incurs heavy computational overhead. Consequently, efficiently leveraging expressive diffusion priors for robust, closed-loop interaction remains an open challenge. To address this, we introduce NaP-Control, a framework that adapts a pre-trained, task-agnostic diffusion policy by training a RL policy to navigate its latent noise space. This formulation enables superior inference speeds and success rates across diverse locomotion tasks and unseen terrains compared to existing diffusion-based baselines, while preserving natural motion and eliminating expensive test time optimization. Framework. We first pre-train a task-agnostic diffusion behavior model to serve as an action prior, grounding policy rollouts within a high-fidelity motion manifold. By conditioning on proprioceptive and action history, this prior iteratively denoise latent noise to generate consistent chunks of future actions and predicted states. The NaP-Control framework treats a pre-trained diffusion prior as a structured action manifold rather than a fixed generator. Instead of predicting raw joint torques, the navigation policy π-theta maps the character's proprioceptive and environmental state to a latent noise space. This noise is processed through a DDIMOD solver to produce a sequence of task-aligned latent actions, which are mapped to the joint level via a frozen decoder for physics simulation. Following RL training, the resulting navigation policy can effectively traverse the latent manifold to identify optimal noise, enabling the generation of natural, task-driven motion while leveraging the full expressive power of the diffusion prior. We begin by demonstrating the capabilities of our method across diverse tasks. Our approach allows an agent to reach faraway goals while maintaining long-horizon stability on flat ground. Furthermore, we show that although a pre-trained diffusion prior may fail to maintain balance on uneven terrain, its motion manifold still contains viable motions that can be leveraged for traversal, including stairs and slopes. We also demonstrate motion agility and reactivity through a right-hand reaching task with frequently changing targets sampled from all directions. Additionally, we evaluate a velocity control task where the agent tracks time-varying target speeds and directions. Notably, the model generalizes to uneven terrains not present in the diffusion prior's training data. Finally, we show that our method can handle contact-rich interactions, such as the task of sitting on a sofa. To validate these results, we evaluate our method against several representative physics-based character control baselines. These models all share the common objective of generating natural motion across various downstream tasks, using different architecture, including diffusion and reinforcement learning. In the far goal-reaching task, pulse exhibits erratic arm swing and unnatural stops, while closed turns abruptly toward the goal and suffer from severe jitter, especially in the hands and feet. Masked mimic displays highly unnatural walking and fails to turn toward goals located behind the agent. Despite leveraging an adversarial prior, CML still exhibits noticeably stiff and rigid motion. Similarly, UniFiz occasionally shows unsteady footsteps or takes detours while reaching the goal. In contrast, our method produces smooth, high-fidelity motion while maintaining a success rate on par with pulse. We observed similar results when adapting to uneven terrain for pulse, masked mimic, AdaptNet, and our method. This is a task that UniFiz and closed were unable to perform. For the agile hand-reaching task, pulse and masked mimic both exhibit substantial jitter, foot skating, and unnatural turns. While UniFiz and close fail this task entirely due to insufficient fine-grained control, our method demonstrates excellent temporal coherence and smooth whole-body coordination, including sidestepping and squatting. These results remain consistent when the agent is placed on uneven terrain. Uniphys and Close were unable to perform this task neither. In the velocity control evaluation, Pulse produces high jitter and unnatural running poses to meet velocity targets, while masked mimic moves with very small steps and a lowered head. Uniphys provides smooth motion and transitions but suffers from high velocity error. Our method, however, maintains smooth motion and reactive turns while accurately respecting target speeds and directions. Furthermore, our framework generalizes effectively to unseen, uneven terrains. In contrast to Pulse and masked mimic, our method ensures smooth transitions during dynamic speed adjustments, such as decelerating from a fast run to a slow walk. Finally, in the object interaction task, Pulse produces awkward upper body twisting, while masked mimic suffers from frequent falls. Uniphys is unable to perform this task at all, and Close exhibits severe jittering. By comparison, our method achieves natural, human-like sitting motions, demonstrating superior stability and contact-rich coordination. In summary, we introduce a reinforcement learning framework that adapts pre-trained diffusion-based action priors for physics-based character control by navigating the initial noise space, an approach that effectively incorporates environmental feedback to achieve faster inference and higher success rates across diverse tasks while preserving natural, human-like motion fidelity.